next this Monday. I mean, coming Monday, I guess. Okay. Okay, so let me start with this thing. Last time, what we saw in the class was that human genomic DNA, human DNA has lots of repetitive sequences, right? And these repetitive sequences fall into different families. One class are called as satellite DNAs, and these satellite DNAs have, the repetitive sequences can vary anywhere, from 1,000 to 6,500 base pairs, and they get repeated many number of times. And then you have what are called as microsatellites. Microsatellites are again repetitive sequences, but these are of shorter length, anywhere up to 100 to 100 base pairs or a little more than 100 base pairs. Again, they are found in multiple copies. And then you have what are called as mini satellites, right? Mini satellites are sequences that have anywhere between 2 to 6 sequences that get repeated. And then again, these repeats can be, variable number of repeats are found in, different people. And it is precisely this typing of these variable number of repeats that helps us to identify, each person's identity. Okay, and we also saw that each of us are inheriting one copy of chromosome from our father, one copy from our mother, and each of these repeats can have different number of repeats in father's chromosome and in mother's chromosome. So eventually what we will have is a unique combination of these repeats from the parental chromosomes, and this is what is exploited in the DNA fingerprinting technology. Okay, so let's just go back to the last couple of slides that we saw in the last presentation, and then we will continue from there on. So does that make clear that all of us inherit one copy from the father, one copy from the mother, and the repetitive sequences that are found in the paternal chromosome and the maternal chromosome can be very different. And when you do the typing, then you will get to know, whether what kind of pattern you have, and that is how babies are assigned to biological parents when there is a case that is lodged in the court and all that. We will see some examples in today's class. Okay, let me show. Okay, this is what we discussed in the last class. Okay, so the Federal Bureau of Investigation in the United States has taken 13 different STR loci, okay, short tandem repeat loci for DNA fingerprinting. It's a mix and match of alleles that occur frequently and some alleles that occur very rarely. Okay, there is a mathematics behind this. Any allele that occurs frequently in the population, right, has certain frequency, and any allele that occurs rarely has a very, very rare frequency, or the frequency is fairly less. And so when you want to discriminate between two closely related individuals, a combination of these frequent alleles and a rare allele is going to give you a very, very high discriminatory power. So these are the loci with different frequencies, right? Some are like fairly low, right? 1.2%, and some of them can be as high as 9.6%. So you have a mix and match of these different alleles, okay? And typically, if you look at the product rule, which is a common mathematical rule, the for a person to have exactly the same loci or same genotyping at all the 13 loci is literally, it's like 1 in 7.7 quadrillion people. Okay, which is not the population right now. The population is much below that. Okay, which means the discriminatory power of DNA fingerprinting is fairly accurate. It can pinpoint an individual in a very, very clear fashion. The population of US, or for that matter, the population of India or China, are much lower than this figure. So if somebody commits a crime, and you can still figure out who the person did, as long as you are able to get hold of some kind of a biological material. It could be hair follicle, it could be, a blood spot, or it could be another biological fluid. Okay. Okay. So I'm going to show you some schematics of this DNA fingerprinting. Is the slide visible?
Yes, sir.
Okay, okay, okay. So this is just showing you an example of just two parents, okay, maternal and paternal homologous chromosomes, and they are looking at only one loci. Remember, FBA looks at 13 different loci. We are looking at only one loci for the parent, for mother and father. Okay, when you do a PCR for this loci, and when you run a gel, right? You can see this repeat. The number of repeats is smaller. The number of repeats is much higher in the maternal chromosome. So, okay. So, maternal chromosome shows you a banding pattern like this, and the paternal chromosome shows you a banding pattern like this when you run agarose gel, because this has large number of repeats relative to the paternal chromosome. This is going to migrate slowly in the agarose gel compared to the paternal one. So the paternal one moves faster and the maternal one is slower. Now this is an ideal situation. This is an ideal situation. Imagine this parent himself, the paternal this thing himself was derived from his mother and his father. So ideally, it's a very rare case for them to have exact identical repeats. It could vary, but this is, as I said, this is an ideal case. Okay, so you see a single band. Okay, in all probability, in real world, you will actually see two bands for the parent, for the maternal chromosome, two bands for the paternal chromosome, depending on how these repeat sequences are structured. Okay, in this case, as I said, this is an ideal case where the father and the mother inherited chromosome with exactly the same number of repeats, which is ideally not the case. Okay, which is not the case in real world. This is an ideal case. Okay, now let us look at a sample. Okay, now this is a forensic sample from, say, let's say from a crime scene, and three pairs of chromosomes are depicted here. Okay, and these are three suspected individuals. Okay, individual A, individual B, and individual C. Okay, so when you do a PCR, so this is an ideal world. Okay, this is the real world example. Now this person has this repeat, so you're trying to do a PCR. Okay, the regions around this are conserved, so you're trying to do a PCR. So when you do a PCR for the forensic sample and when you run agarose gel, you will get 6 bands, right? 1, 2, 3, 4, 5, 6 bands you will get. Okay, you have 1, 2, 3, 4, 5, 6 bands. All right. Now, when you do a PCR for all these three suspected individuals, you will get a banding pattern somewhat like this. Now, looking at this picture, who do you think is the person who committed the crime? Any idea? Is it A, B, or C? F is the forensic sample. Is it A, B, or C? Okay. If you see an identical match between the forensic sample and your suspect, okay, then it is highly likely that B is probably the suspect. If you look at A, for example, A, there is a mismatch. These two don't match, right? The rest of it are kind of matching, but these two don't match, okay? If you look at C, C doesn't match at many of the this thing. It matches probably in this region and this region and this region, but it is again not matching in all the regions. If you look at B, B matches exactly with the forensic sample lane by lane. Fragment by fragment, you see a exact identical match. That is why B is suspected to be the person who could have committed a crime. Okay. Did I make it clear? Did the reason become clear?
Yes, sir.
Okay. Thank you so much. Okay. So this kind of a thing is typically used when you have a paternity dispute. Okay, we will see in the next slide. Okay. I think if I put it on a slideshow mode, it seems to be having some issue. Am I audible?
Yes, sir.
Okay.
Yes, sir.
Because my slides are not moving. Give me a minute. All right. I will not put it on slide mode. So, okay. Is it a little better now?
Yes,
Oh,
sir.
very, very. Okay. So, okay. So DNA fingerprint of children share a lot of similarity to the parents. Okay, the DNA fingerprint that you would see in the children is exactly, you would see a lot of reflection between what you see in the parents. Okay, I'm showing you an example here. There are 5 pairs of adults. Okay, adult 1, adult 2, adult 3, 4, and 5, and there are 3 children. Okay, 1, 2, and 3. Okay, these are the DNA fingerprints for the parents. Okay, 1, 2, 3, and then you are trying to identify, which child belongs to whom. Okay, so you can actually see that child 3 shares a lot of similarity to adult 1, right? You can see that child 3 shares a lot of this thing to adult 1 and adult 3. So it is possible that adult 1 and adult 3 could be the parents for child 3. You see the reason? You have a father and a mother, okay, and you can see that child 3 belongs to, adult 1. In these loci, you see a match, right? And then adult 3, child 3 has also, match with adult 3. Okay, so this is a complicated case where, people marry, divorce, and then they remarry to another person. So you have stepchildren, stepfather, all those kind of complications. Otherwise, the normal case, you will not see that. Okay, normal case, you will see a straightforward this thing. Okay, child 2, for example, again you can trace back to adult 3 at this thing. Child 2 also goes back to adult 1, right? Um, Child 1, on the other hand, you will see only with adult 1. Okay. I'll give you the exact details maybe a little later. Okay, but actually what you see here is a mix of adults and children, and looking at the fingerprint, you will be able to identify which of them could be the parents. So obviously, none of them match to adult 2, none of them match to adult 4 or adult 5. Okay, so it is probably adult 1 and adult 3. Okay, all the children belong to adult 1 and adult 3. It's not to any of these. So typically in a paternity suit, when which is common, when two parents claim the ownership of a baby, all that they do is you will have adult 1, adult 2, adult 3, and adult 4, right? Two parents. Okay. You will do a fingerprinting, and then you will also have the fingerprint of the child. Okay. And they will closely look at the DNA fingerprint of the child matches which of the parent. Okay. And the parent to whom it matches, the child is given to that particular parent, which has been solved. I mean, this is not something unusual. It has happened many a times in India. People have babies have been swapped, and then when people realize that the babies have been swapped, they go back to the court They raise a case, and then DNA fingerprinting has solved a lot of these problematic these things. Okay. Okay. The first crime that was solved in the world using DNA forensics happened to be in England, where the entire technique was, first put to use. Okay. So this was in the 1983. Okay. There were a series of murders. Okay, and sexual assault and murder of a girl in the United Kingdom. The police picked up a suspect, but the DNA did not match with that of the suspect at the crime scene. By then, by 1983, it was kind of people are moving towards DNA fingerprinting, and police collected about 5,500 samples from the area's population of likely suspects, but none of the DNA profile matched to what was seen on the crime. Okay. It turned out that the friend of the suspect had given a sample in the name of the suspect. Okay. Although the suspect was picked, the suspect didn't go to give the sample. Instead, his friend gave the sample, and that's how he escaped. Okay. In the year 1983, there was a rape and murder of a 15-year-old girl in one of the counties in UK. Okay. 1986, nearly identical case in a nearby town. Okay. And the police suspected and they focused on a young kitchen worker with a low IQ who ultimately confessed to the second crime. Okay. But unfortunately, DNA from the crime scene did not match with that of the kitchen porter. Okay. And so obviously he was exonerated. Then, as I said, about 5,000 men were subjected to testing. They did both blood grouping and DNA profiling. Blood grouping has a very low discriminatory power, right? Blood grouping, there are only four positive possible types: AB, and O. If you do finer discrimination, you may have, A negative, B negative, OB, AB negative, but and O negative. But that doesn't really give a high discrimination. Okay. And this guy called Colin Pitchfork avoided mandatory testing. Okay. He claimed several legal rules and say nobody can force me to give my sample. But ultimately, the courts had to intervene, and the courts made it mandatory to give the DNA sample. And in 1987, it took about 3-4 years for the courts to pitch in and force this person to give the blood sample. And when it was tested, this guy called Colin Pitchfork turned out to be the uh, uh, the person who did the crime, and not the kitchen porter. Okay, because he had low IQ, and this thing, extreme pressures. That guy probably confessed to crime. We still don't know, but of course, from 1983 to now, a lot of legal changes have happened, and so nobody can force you to confess your crime. Legal laws have been strengthened. So anybody who's picked up as a suspect, he need not confess. And if he were to say that I gave this confession under extreme pressure, then the courts can actually, remove that confession. Okay. Okay. There was another incidence of this thing being used in the United States. Okay. This is called as the Forest Hills Rapist case. The DNA was first used in United States in 1987. They were a little bit behind the United Kingdom in using this. There was a guy called Victor Lopez who was tried for sexual assault of 3 women. Okay. The reported assailant was supposed to be a black man, but Lopez was not a black man. He was Latino. Okay. And the DNA was a match to the crime scene. So eventually, Victor Lopez was tried, and he was found to be the actual suspect. Okay. Large-scale DNA fingerprinting came to the fore during the 9/11 time, when the World Trade Center was attacked. Okay. Literally, so many people died in that entire incident, right? And in that terrorist act, many people were beyond recognition. Okay, people saw bits and pieces of flesh. Okay, and with a lot of discussions and all that, those remains were saved. Okay, those remains were saved, and they did DNA fingerprinting on those remaining whatever flesh they could get. It could be parts of the hand, could be parts of the any part of the body. Whatever they found, they did DNA fingerprinting, and that was used to identify the remains of the victims. Okay, there was a lot of debris, heat, and a lot of the highly decomposed bodies were found. But nevertheless, whatever little DNA they could salvage, they used that. Okay, hundreds and thousands of tissue samples, were retrieved from nearly 3,000 individuals. They were matched back to the. It could be a son who could have died on that day. He was that was traced back to the parent. A parent could have died, so the son or daughter's DNA typing was used to trace back the parent. Everybody knew, that people went to work on that day, 9/11 on that twin tower, and they knew who they were, right? The parents knew whether the children are gone, or the children knew whether the parents have gone there or not. And so they went back and forth, and then they could eventually figure out more than 90% of the thing was handed over. Remains were, in some cases they only found a few body parts, probably few fingers or maybe a small piece of flesh, and that was handed over to the relatives for their ultimate religious ritual. Okay. So within 24 hours, of this 9/11 tragedy, very quickly the government acted. The U.S. government acted very quickly, and they organized, collection points around the city. The families filed missing person report, and the family members gave their cheeks cells as swabs for DNA isolation. Okay, and personal items from the missing people were also collected. Okay, so this was a massive disaster, massive disaster. Okay. Around of the 2,753 people who were reported missing, okay, 1,113 people have never been found. For the remainder of the people, whatever, as I said, a small piece of flesh was found, and this was a massive operation of, unimaginable this thing, I think police dogs, sniffer dogs were employed to trace out remains of human DNA. Okay, and whenever human DNA, human flesh was found, it was saved. Okay, it was given an ID, it was saved, and then eventually it was a small proportion of it was used for DNA typing, and then the remainder was saved until they could identify to a close relative, and then it was handed over back to them. Okay. Another case where DNA fingerprinting was used was in the South Asian tsunami. This happened in December 2004. It hit parts of Asia, and particularly India, Sri Lanka, and some of the other countries. Okay, we were hit hard. I think Malaysia, Indonesia were also hit hard, and close to 225,000 people were, lost their lives. Okay, and so in those cases, they were by then, the 2004, the technology had advanced even further. So mitochondrial DNA and Y chromosome STRs were used for typing, and then hand over the individuals. See, many times what happens is when something like this happens, the governments will say that we will compensate the victims, right, for their tragedy. And any time when a government says that we are going to compensate, there are going to be a lot of fraudulent cases that are going to come up and claim the money. To prevent that, the government stepped in and they said, unless there is a DNA matching, they will not be able to give the claim. Okay, so that is why this was done. And also I think in the end, when somebody wants to have a closure, right, when they want to have a closure of all these things, they want to make sure that they are holding to their near ones and dear ones, and they want to do their final ceremony. So this turned out to be very, very useful. Okay. How do they do fingerprinting in paternity testing using microsatellites? You basically they extract DNA from the small this thing. They will do a small amount of collect a small amount of blood. It could be from a fingerprint. Okay, from the mother, baby, and the fathers. Okay. They synthesize oligonucleotide microsatellite primers and label one primer with the fluorescent dye. So you actually use two primers, right? One for the forward PCR and the one other one for the reverse PCR. Okay, these microsatellites are amplified using PCR from the mother, the baby, and the father. Then you would run a agarose gel or acrylamide gels, depending on what kind of this thing you're looking at, along with the fluorescent size standard. And 3 to 4 different microsatellites can be multiplexed because the sizes, as you can see, are different. And then each the size of each microsatellite relative to the reference standard, okay, can be calculated. And sometimes they might sequence at least one copy of the each allele to verify it. Okay, so this is a typical example. This is a fluorescent standard they have run. This is the microsatellite of the mother. Okay. This is the microsatellite of the baby, and this is the microsatellite of the father. You can actually see that the baby has one from this father and one loci from the mother. Okay. So this is a hypothetical gel pattern. Okay. When you have paternity testing, then typically baby and mother are expected to share an allele, and baby and the father is expected to share the other allele. The baby is going to get one half from the father and one half from the mother. That's why you will see one band. If you see in this case, only one band matches, right? So the baby got this particular repeat from this chromosome, and the baby got this particular repeat from the mother in this chromosome. Okay. So the baby and the father do not share a common allele, then the father is probably not the father of the baby. This is typically the case when people are getting married, divorced, then getting remarried. Many of those complications. This is typically the case when you have those kind of situations. Okay, if the baby and the father do share a common allele, paternity is possible, but not proven because other men in the population also carry the same allele at some frequency. That is why they use certain things, alleles which are of rare frequency and alleles with high frequency. Okay. Frequency of the alleles that are shared in common by chance can be calculated, and an appropriate number of microsatellites can be analyzed to calculate the probability of paternity. To achieve a high probability, as we saw, FBA uses 13 different loci for DNA typing. Okay. But for paternity testing, you probably don't need that much. Okay. You can probably do as many as up to 6 loci, generally up to 6 loci. Okay. But again, the exact number depends on variation in the population for each of those genetic markers. Okay. So this just shows you a calculation, if it's a common, then it is like, you have the frequencies of the order of 10 power 8. And if it is 12 loci, then it gives a probability of this thing, ID, of 10 power 16. Okay, but if you mix and match, you're going to have even higher discriminatory power. Okay, so that is how a combination of biology, mathematics, statistics, all these are used to identify and solve these kind of issues in forensics. Okay, I would like to stop at this point, and if there are any questions, I can answer those questions. Otherwise, I don't think we should start another. I don't want to start another session. Okay, we'll do the types of PCR probably in our next class. Okay. Okay. Any questions? You could use, for example, when somebody is smuggling, for example, say some rare endangered species are smuggled, then people could do a simple DNA typing and go back and show. See, some of these things are now stored in databases. You don't need to do this again and again. Okay. For example, if you know that a tiger or a cheetah or any of those plants or animals are endangered, all you need is a small bits of their this thing tissue, and you could do a PCR, and now you can store all these things in the database. Okay, tomorrow or any time when somebody has a sample, then you can go back, you can analyze the sample and do the same fingerprinting for that, and if it matches with your database, then it is probably an endangered one. If it is not, then probably you can let them out. The how this entire thing started was, whales are supposed to be on the endangered list, right? So there was a ban on whale meat, okay, and when Alex Jeffrey was trying to devise how to know whether this meat is of whale origin or not, there are a lot of work that had been done earlier on myoglobin. So he started looking at protein fingerprints, okay. Then it turned out that myoglobin is probably, shares a lot of similarity to hemoglobin, although it's little different. It turned out that they were not able to differentiate between those things at the protein level. Okay, so then the question was, can we use DNA? And then it turned out that DNA had a much higher discriminatory power. Okay, and that's how this entire fingerprinting thing started. Okay, but now of course we know that the mini satellites, which are repeats of 2 to 6 base pairs, are predominant in the genome, and it's very quickly it can be done. PCR can be done and can be used in the diagnostic purpose. Okay, diagnostic in the sense can be used to solve or can be used for typing the DNA of a person. Okay, any question? Okay. If there are no questions, then probably tomorrow we will have a class on professional ethics. Okay. I will let you all know when we will have. We will have a combined class with the PG students. Okay. The initial portion of the syllabus same. So we will have a combined class tomorrow, and then we will, probably start having individual classes later on. Okay.
Okay, sir.
Okay, sir.
Okay. Thank you. Okay. Yeah.